Okay, so let's continue on with insulators. Insulators do not transfer heat well by conduction, meaning that they're a great way to keep heat in or heat out, depending on what your goal is. Gases and nonmetals are good insulators. Um, Sorry, I went back the wrong way. Because gases are good insulators, most windows are now made with two panes of glass with an air space between them. This is also how some of those heat preventing, I guess, tumblers are made, where you have the glass that's double walled. And in between those walls is nothing, it's just air. And what that air does is it helps to protect the liquid that's inside, usually it's iced, from absorbing heat as quickly. They also advertise these as sweat-free, because it's usually the change in temperature or the fact that the outside of the glass got so cold that causes the air to condense on it. So anyway, that is the insulator that is used in that kind of a glass. Now, a lot of times when you see windows, because a lot of windows are double pane, they have air between the panes, they are advertising as having an R value. And has to do with their insulating abilities. You'll also see this on the rules of insulation that you put into your walls or in your attics. Combining the insulating abilities with the thickness of the material gives the R value. So if you don't use it the way that they say, you used half as much, you aren't going to get the same R value that is listed on the material unless you use it the way the manufacturer says. Aerogel, there's actually a facet in your textbook and it's blue. Aerogel is the world's lightest solid substance. It's the best known insulator that we have today. It's also one of the most expensive, which is why you can't buy aerogel in your local supermarket. But in the facet, if you go and look at the picture, you'll see that they have a blowtorch against an aerogel. And there's crayons sitting on top of the aerogel that are not melting, even with a blowtorch on the bottom of it. So I think, though, until they find a cheaper way of manufacturing this material, this will not be found in a supermarket near you. All right, thermos bottle. A lot of people have these. Thermoses are an excellent insulator. They have tight seals to prevent convection, meaning that the heat's not going to rise out of it. They're also usually silvered to reflect radiation. And then the empty space between the casing and the outer can prevents conduction. When I was growing up, a lot of thermoses were made of glass to the inside because glass is also a very poor conductor. All right, some of the questions. Heat in a house is transferred mainly through, think of your answer, convection from your heating or cooling system. Heat is transferred on a stove through, think of your answer, conduction, because it's touching it. All right, let's get into the meat of this. Heat capacity. Heat capacity is the thermal energy in joules that an object must gain in order to change its temperature by 1 degree C. Its unit is joules per degree C. We are usually writing heat capacity as this. Okay. A large object of the same material has a higher heat capacity than a smaller object of the same material, and that's because they may have written those units like that, but that is not the entirety of it, because you have to take into account the per gram of the substance. This means that the value is specifically for that substance alone. So every material is going to have its own specific heat, and I will always give that to you. I'm not expecting you to guess, or you will have enough other information that you'll be able to calculate it. Okay, so this is how, see, they just told you that the other unit was right, but no. You had to have the grams. So C, the units are joules per gram times degree C. Okay, so here are all the things labeled. M is mass, and it is in grams. Delta T is the change in temperature. Please notice the units. It must be in degrees C. And the last value is Q, which is heat. The formula that I like is this one, and I usually call this Q equals MC delta T. And this is to find the heat necessary to change the temperature of an object for a certain amount. Okay, that's how that works. We will have several examples of these in a second. This is a calorimeter. We won't be doing one of these. However, when you're in chemistry, you will get to use one of these and do a great calorimetry experiment. All right, sample problems. How much thermal energy must be added to a 723 gram piece of steel in order to change its temperature from 30 degrees to 420 degrees C? So here are our knowns. So remember, mass, this is the M portion. The specific heat is 0.5 joules per gram degree C. The change in temperature, okay, so they didn't have that in the problem. Here is the specific heat they hadn't given you before. Change in temperature is going from 420 or from 30 to 420. Remember, delta T is T final minus T initial, because here we're looking for an addition of temperature, which means you're expecting Q to be positive. Unknown is heat Q. So here you go. I'm going to write out the formula again. Okay, and then let's go through and plug all that stuff in. Q equals MC delta T. So you plug them all in. Mass, here's your specific heat, here's your temperature. I'm going to write it up here so you can see how all the units cancel out. 0.5 joules per gram degrees C. Remember, these are unofficially over 1. Give you some perspective for the math. So grams cancel, degrees C cancel. All you are left are the units joules, which is what you want for Q because the units of Q are always in joules. So then it's just a calculator problem. You're going to multiply 723 times 0.5 times 390, and you get 140,985 joules to raise that 723 grams of steel from 30 degrees C to 420. Okay, and then of course they rounded up. We're not doing the significant figures, don't worry about that. Specific heat capacity. So water has a high specific heat. Look at it compared to, so here's water, 4.18. Here's everything else. Acetone is like fingernail polish remover, alcohol, ammonia, gasoline, 2.2. Vegetable oil, look how low that is. Propane, 2.4. Okay, water has a pretty high specific heat. All right, we talked about this in class. I'm going to click through this pretty quick because I want to get to the problems. Feel free to pause at any time if you feel like you want these notes in more detail. Does water at room temperature heat up if you add thermal energy to it? Of course. Does water always heat up? No. And I did these in class. There is no change in temperature during a phase change. The energy is used to break or form the bonds. This means there's no temperature change when water is freezing, melting, boiling, or condensing. So, the latent heat of fusion, and this is for the melting or freezing, okay? This energy is used to break or form the bonds of a solid. Water has a high heat of fusion, which is why a little bit of ice can cool so much water. So this is the graph that I drew in class, okay? So this is just the melting portion. So you have ice here where thermal energy is being added here, temperature is rising here. So we're adding thermal energy, but in this phase of mixing where there's some ice and some water, when it is either melting, and remember this can go the other way, or freezing, there is actually no change in temperature during that process. And here, that was the latent heat of fusion for water is 333 joules. The latent heat of vaporization is during boiling or condensing. So when you get to the point where water is hot enough to boil or is cooling down to condense from a vapor, then you have to use that energy to break those bonds. And so here's that graph. Same thing. That takes a lot more energy because obviously you're moving these molecules away from each other. 2,256 joules to make that change. Every substance has a separate value for specific heat. latent heat of fusion and latent heat of vaporization. If anybody is at all interested, I have a book that has them all listed in case you're curious, but they're there. To find out how much thermal energy must be added in order to boil a liquid, you use the formula below. So when you're using the, and this works for latent heat of fusion as well, you're just using the mass and then the latent heat of vaporization or fusion. Those are interchangeable values. The formula doesn't change. Let's look at a sample problem. How much thermal energy must be added to 375 grams of water at 100 degrees C in order to change it into steam? So you have the mass, you have the latent heat of vaporization, and you want to know Q. Well, here's our formula. Q is mass times latent heat of vaporization, so it's just a math problem. Remember too, again, that we're setting these up as fractions. Joules per gram, the grams cancel out, so you end up with joules as your unit, 846,000. All right, that was the end. If you have any questions, please let me know. I'll be available for the questions, and you have all of those sample problems that I assigned in class all the way to the end, and we will see everyone later.